So the present value that you have here gives you the present value basically 1 year before the first cash flow appears. So this one here, we should annotate this using time subscripts. It's not really precise here. So this is the present value at time 0, and the first cash flow is in year 1. Right? So you can always apply this formula for any stream of cash flows whenever it starts, but the value that you get is the value occurring 1 year before the first cash flow. So we can use the formula actually to compute the present value of these things, but it will be the present value at time 25. And then what we can do is we can do discounting again, and we can discount it back to year 25. So let me kind of write this down in terms of a formula. So the present value of the bond at time 0 can be now computed out of several things. So first of all, we have to deal with the notional amount. So how much is that? That is 1,000. The payment is made in year 25. Let's add the notional here. Let's have it complete. So the notional is just 1,000 euros here. So the notional is 1,000, and we discount this at our rate of 12%. And then we have to raise it to the power of 25. That's the present value only of the thousands. And then the coupon payments can be expressed as the value of the perpetuity minus the value of the difference. Right? So these two lines, perpetuity, the coupons plus difference give the perpetuity. I should write this down here. So coupons plus the difference term here. These two cash flows together equal the perpetuity. Or in other words, the coupons, the value of the coupons is the value of the perpetuity minus the present value of the difference. And that's exactly what we're going to do here. So let me write down the value of the perpetuity. The value of the perpetuity is 50 divided by 12%. That's the perpetuity, our shortcut formula that we studied last week. And now I need to figure out what the present value of the difference is and subtract that. So this is going to be minus. Now how do we do this? Well, it's a two-step approach. The first thing is we apply the perpetuity formula on the difference, so that's 50 divided by 12%. And 50 divided by 12% is the present value of the difference at year 25. To make this the present value today, we have to discount like we did here. So the present value of the difference is the perpetuity value divided by 1 plus 12% raised to the power of 25. So this thing here, these two terms, that's the formula for the annuity. And that might be something that you see somewhere in textbooks. Maybe kind of, let's write this down here in a formula. So that's your cash flow X divided by the interest rate R multiplied by 1 minus 1 over 1 plus R raised to the power of T. That's the annuity formula. So this is taken out of this fraction here because it's the same in both terms. If you take it out, then in the parentheses you have 1 minus to discount that. This is an annuity with annual payments. Right, so it will be slightly different if you have a kind of a loan and want to use this formula here. You have to put in here for R, you have to put in the monthly interest rate. And in the exponent, you have to kind of use the number of payments that you make throughout the whole lifetime of the loan. And X will be your loan amount, right? That would be the amount that that would be your monthly payment, and the present value would be your loan amount. So there's some weird formulas for the annuity that you find in textbook, but I think that this way is kind of the best way of remembering it. So I actually don't remember the formula for the annuity, I just remember the perpetuity formula, and I know annuity is the difference of two perpetuities. That's kind of the intuition. Right. And this is something that you can now easily plug in your calculator. These numbers are even the same here. The discount factors here and here are even the same, so it's something that you can quickly compute with the calculator. So the result is going to be 450.98. So my undergrad courses, this is like a nice exam questions because, well, obviously I choose a number of years that students can't start putting up 25 or sometimes even 50 or something turns. So they quickly realize, oh, that's too time consuming. And then the only trick they have to figure out is that, oh, I have to apply the annuity formula here. And of course we discussed the annuity in class a little bit longer than we do today. So look out for contexts where you might be able to use this. So whenever an annuity is a constant cash flow, which ends at some point, the perpetuity goes on, the annuity ends. And you can do this monthly or annual. So this is the annual annuity here. But it's pretty easy to get to the monthly formula. Just plug in for R the monthly interest, and for T, you would plug in the number of payments that you have. So this T here is the number of years. So you multiply that by 12 for monthly payments. So I actually believe that we don't really have a context where we're going to use the annuity here in class, but it's an important formula, and I want to show you how you can apply the perpetuity formula as we discussed last time. Not really realistic cash flow, but annuities are pretty realistic, right? So, and for your personal finance, if you ever take a loan, you will kind of go back to this formula.
5% nhân với 1.000
look it up
bằng
and kind of
50.
calculate your monthly repayments to the bank based on how much you borrow and what rate the bank offers to you. The interesting thing in this loan example is that the monthly amount that you pay to your bank is a constant amount. However, your loan, the amount that you repay is basically made up of two components. The first part is the interest, and the second part is a repayment of the loan amount, which you regularly do every month. Now, when you repay some amount of the loan, your interest payment goes down, right? However, the loan is designed that the total payment is always constant, but the split between the two these two components is going to change over time. So your repayment is going to increase over time, and your loan is increasing, and your interest payments are decreasing over time. And this formula designs it in a way that the sum of those two is always equal, and that you will basically have repaid the full loan at the maturity date. Right, so X is here the monthly repayment, and make sure, or this formula is used such that you will exactly end up with the loan amount of 0 at the maturity date. Right? You will have repaid everything throughout the lifetime. So that's why it's so popular with banks, because there are these constant payments. If you ever want to figure out how much of a house or apartment you can afford, you can also use this formula. So just plug in for X the amount that you can spare per month for an apartment. So I would use the cold rent at the moment because you would have to pay heating and so on, no matter whether you're renting or buying, right? But if you're buying, you save the cold rent, right? So that would be the amount that you can afford to pay to the bank, right? So just plug in for X, plug in the value that you're able to afford, say, when you have maybe a regular income, it's 1,000 euros per month, right? So make the monthly repayment X equal to 1,000. Look at what the interest rate is. At the moment, it's not so attractive. They went up from 1% at the beginning of the year to 4% at the moment, so they quadrupled, right? So then you would plug in 4% divided by 12 here. Then you would have a typical loan length of 20, 30 years or so. Just plug that in. And then compute what the present value is, and the present value is the loan amount that the bank is willing to give you, and that's basically the value of the house that you can afford. Right? So if you ever want to know kind of what your budget is, if you're looking for purchase of an apartment, use this formula. Right? It's directly giving you the answer. So I think it's a very neat application and a and a used practical application. Okay. Any further questions regarding the annuity here example? So then let's come to the second example, that would be evaluation of equity, which is a context where you can justify the application of the growth formula. First of all, equity doesn't have a maturity date, it doesn't expire, right? So the infinite time horizon now seems okay. And if you simplify this, you say, okay, the stream of cash flows that I get from my shares is the dividends. And for simplicity, we assume that the dividends are growing at a constant rate. So it's very straightforward.